So, we have then we look at input modules. Input modules basically convert process level signals to processor levels. So, what do we mean by process level signals? Process level signals are signals which actually exist on the field. For example, they could be 24 volt DC signals or 230 volt AC signals, or even sometimes contacts, sometimes some RTD, platinum RTD, or could be a 4 to 20 milliampere current loop. The signals which actually come out of sensors, right, sensors and actuator devices. So, these a PLC is an electronic device, it is actually a digital electronic device. So, it as such cannot take in that kind of electrical signal. So, it must convert them to processor level signals which are digital, typically 5 volt or maybe 2.5 volt, whatever. So, that job is actually done by the input modules. So, their job is to basically translate process level signals to processor level signals, also convert them from analog to digital sometimes, if they are not always digital. So, the jobs are mainly, another important thing is to provide isolation, because the electronics, if you expose digital electronics board to 115 volt or 230 volt AC directly, chances are that it will get damaged. So, you have to provide electrical or galvanic isolation using optocouplers. So, input modules very often provide that. They provide fault indication, suppose some wire has broken, often they provide fault indication. This is apart from converting process level signals to processor level signals. They are generally of two types, they are either analog inputs or digital inputs. We understand the difference between them, right. So, for example, a contact would be a digital input and a platinum RTD would be an analog input. So, obviously, we need, for the analog input modules, we need to have analog to digital conversion, typically 12 bits accuracy, multi-channel sometimes. One input module generally supports several physical one input module supports several input channels. So, there, since each digital channel actually takes 1 bit, while each analog channel could take as much as 8 or 12 bits. So, therefore, typically an input module will support 32, 64, 128 kind of digital input channels, while it will support 8, 16 or 32 analog channels. These are just some typical values. Similarly, sometimes it takes special inputs, like you can directly connect thermocouples, you can directly connect RTDs. So, inputs can be in the form of voltage, current, resistance, etc. Sometimes it can be in the form of pulses, for example, a shaft angle encoder can be sometimes connected. So, this is the nature of input modules. Then we have output modules, they do the reverse, they translate processor level signals to process level signals. They are output devices, and these process level signals then go to things like motors, solenoid lamps, valves. They have to actually do work, right. So, they have to be converted in form, generally they have to make, sometimes mostly they have to be made analog, or sometimes even on off kind of signals, but they have to be increased in power because they are supposed to do work, right. So, they also provide isolation, and for analogs it has to provide the voltage or voltage and current drive. So, typically a unit that will provide that will be a, let us say, a servo amplifier. So, such amplifiers will be put on output modules. For digital output modules, sometimes they will require high power, you will just give a pulse and you will require that during the duration of the pulse there will be a high current will be switched. So, that such a thing will be done by the output modules. It is typically, let us say, using TRIAC or maybe an IGBT. Today one would like to probably use an IGBT, and there could also be potential free relay contacts. That is, sometimes we we do we can do, suppose we want to switch a voltage or current, because it's digital, so it has to be on off kind of thing. So you could actually do it in two ways. One way is to use a device, electronic device which will interrupt. Another is to do a mechanical interrupter. Now, since these currents can be sometimes very large, so therefore you don't directly from the output module you don't interrupt a large load current. You actually use a relay which activates a contactor. So, the contactor is actually a heavy device, heavy contacts, you might have seen them, and they provide contacts, and if you drive those, if you drive a signal into it, then some relay will make the contactor work. So, using a low power signal you can interrupt a high current using a contactor and relay. So, such outputs can be driven from digital output modules. So, let us have look at some of these pictures. For example, this is how a typical analog IO module looks like. Let's see what it contains. So, for example, you will find that there are some analog signal terminations probably here, and there are some bus ports probably here, difficult to see this. Inside you will have, these typically this is an analog, so support several channels. So, there has to be eddy conversion. Typically you do not put, if it's not that if you have 16 channels you will require 16 eddy converters. You will take one eddy converter, and the eddy converter is so fast that it will first convert this channel, then this channel, then this channel, then this channel, and so on. So, it will multiplex the eddy conversion. So, you have multiplex eddy conversion. At the same time you need to ensure that although you are taking the values one after the other, but you would like to ensure that the values that you are taking finally all belong to the same time instant in the process. So, you use xk, yk, zk, all of them are at k time instant. So, for that you need simultaneous sample and hold, where you take the value simultaneously using sample and hold circuits, and you hold them, and then the eddy converter picks them up. And you also have various output drivers, especially for output modules. So, this is the basic, these are the basic thing that an analog IO module will contain, and of course, some logic for synchronization. Then you have a different kind of IO modules which are called distributed, or sometimes called remote IO modules. So, these are actually intelligent field mountable IO devices. So, you actually put the IO module right there on the machine, and from there you draw a wire, or you connect it to a network, or you take an input output concentrator and connect several local distributed IOs, and then make one digital communication back to the PLC. The advantages are mainly in savings in cabling costs. I might have mentioned before that cabling costs are not insignificant part of any industrial automation project. So, and they generally cause inconveniences in an industrial environment. They are difficult to maintain, sometimes may get cut, etc. So, savings in cable costs and maintenance costs are significant. Then they are sometimes, I mean, especially when they are on the network, they are actually programmable from a parameterizable from a processor or a programmer. They have, because they generally communicate with the processor over, first of all they communicate with the processor infrequently, because they are actually intelligent themselves and they can do much of their work. Secondly, they often communicate with using digital communication protocols which are much more reliable. So, you have much improved data integrity, your cost of cable, etc. comes down. So, typically used for applications like very close positioning with analog digital encoders, which requires frequent sampling, frequent slow output generation, very difficult to do it with the central processor because it will get loaded. High speed counters, which needs to count high speed events like fast moving shafts, angle pulses. Some specific loop controllers, temperature control loop, etc., where you just need to download the set point from the central processor, and the basic loop works on the distributed IO module. So, this main processor is not bothered with that. So, that is a distributed I/O, generally getting more and more popular now these days. Then you have some other kinds of modules called function modules. These are not, sometimes they could also be mounted on the machine and make part of a distributed I/O, but otherwise they may be situated on the PLC rack itself, but still they are actually independent modules that can execute tasks independently. So, basically reducing the central processor load, so that it needs to talk to it less often for precision and high speed tasks, and they often have their own logic, their own pre coded control laws, they have their own optimizing abilities. It might tune its own, you just have to give it a command that you tune yourself. So, it has its own code, it will actually tune a control loop. And typical application would be stepper servo control, multi axis synchronization, as we have we will see after just following this. We will go into the manufacturing, the CNC machine controls, where we will find that there are many cases where a precise 2-dimensional motion has to be created. Suppose you are actually cutting something along a surface, so you have to create precise 2-dimensional motion. So, you have to give motions along 2 axes, motion commands, and they have to be very synchronized. So, that is called multi axis synchronization. For such applications, typically you use function modules, specialized function modules, and sometimes they could be also used with distributed I/O systems to be situated on the machines themselves. This is another controller which is a valve control module. I chose this because I wanted to show the power transistors on this. So, you can see the power transistors. So, it has to drive, valve means it is probably a hydraulic servo valve or something, or so it has to pull a solenoid, create some force, so that the piston moves. So, for that it needs to provide good amount of current. So, you have these are the power transistor drives. It takes set point from outside, so it interfaces to the bus, and the central processor gives it the set point, and it has its own onboard controller, right. So, this is a typical valve. This is another picture, a counter module. You can't make out much from the picture except for the fact that you can see certain things, like for example, we need to go back. So, you see, you can see that, for example, this module contain I think 5 counters. So, you see the count value has to be read on the bus. So, these have count values have to be read, then event signals, that is go up, this thing has to come. So, there are probably 5 counters here. On the other hand, it also connects to the bus, so that these signals can be read, generally used for so the count is readable on the fly because it contains dual ported RAM and high speed count. So, generally used for very high speed counts. So, one would have large registers and things like that. This is counter position decoder. See, most counter modules can easily be used because position decoding is often by counting the shaft angle pulses shaft angle encoder pulses that are coming over a certain period of time, or because every pulse will mean a certain small angle rotation. So, if you want to have shaft angle position decoder, it is basically counting pulses. So, some of these some of these can be used for either as a counter or as a position decoder. So, you have pulse inputs, you can count or you can read shaft position, and both they will be readable on the fly, as we said, and for high speed. So, this is just to give you a feel of the PLC system. This is a position control module. So, again position control module, onboard dedicated high speed CPU. Position control is generally requires very fast computation. So, you have dedicated high speed CPU. By high speed CPU means you have CPU with higher capabilities, you used higher order processors. When you have low speed controllers, you use generally you use things like microcontrollers to realize them, while here you could use higher end processor like maybe 68,000 and motor drive. So, on the motor, so it gives there is a drive, there will be a power electronic drive which will be given a set point, and that power electronic drive will realize that set point. On the other hand, it will take its own set point, it will take from the central processor. It has digital I/O depending on what is the final motor, various, for example, for a stepper motor, it is actually driven by digital I/O. So, these are some of these modules which are used in PLC systems. It has a programmer port because you need to, there are a large number of parameters which have to be set and set point comes from the data bus. So, all these modules, how they are connected, that is what are the various data paths. To understand this, you have to understand that the PLC, I am sorry this. So, the PLC is, as we have said, that it is rack mounted, right. So, there are a number of racks, it is like an almirah, there are a number of racks. In each rack there are slots. So, in each slot you can put I/O modules or you can put CPU modules, and in each slot, so this is slot, this is rack, and in each slot contains several channels, right. So, there could be 8 analog channels. So, channels. So, this is how I/O is actually organized. It is rack slot channel. So, if you want to identify a particular physical signal, you have to have a rack slot channel addressing, which is implemented in various ways by various manufacturers. Now, all these racks must be connected. So, they are actually connected at this level by ribbon cables, and then from rack to rack connection is generally achieved. Okay, we will see this in the next diagram. We will see it in the next diagram. So, here you are. So, these are this is one rack, let us say this is one rack, then you can have several racks, for example. So, they are actually connected by what are known as interface units. So, these are interface modules. Similarly, so you can expand your number of modules. Sometimes you can put, as I was telling, that you can put your modules in a different almirah, which is different cabinet. When I say almirah, actually it is a cabinet. So, for that you need to have a special special interface unit. So, typically an interface unit it can be, say, typically such distance for reliable data transmission, such distance requirements are there at a certain rate. So, you can go up to something like 100 meters, which is a lot. And sometimes you can have remote interfacing, that is actually you may be having your CPU in some that is your basic PLC system in some control room, while you have these various interface units in the various shop floors, which could be even half a kilometer away and things like that. So, for such cases you need special interface units which are called remote interface units. So, this is the way that all these elements are actually connected with each other and buses are extended. Then all these things that are happening, one generally wants to get a view of it. So, to get a view of it, you use a man machine interface, and as such PLC modules often work without any intervention from humans. So, as such they have very little MMI capability. They do not have generally contain displays by themselves. They will probably contain some LEDs which will just indicate whether they are functioning normally or not. But if you want to visualize, if you want to monitor what's happening to the various variables, if you want to trend them, show it nicely to an operator, it is possible through the various man machine interface elements. So, you can have operator panels by which an operator can give commands to a variety of devices. Some of them may be mobile, it may be push button, joystick, various kinds of multifunction input panels, various kinds of things. Similarly, he can see it, you can actually connect a PC to a PLC, and on which various kinds of visualization software which will nicely show your plant, and as levels of fluids will go up and down, it will nicely show you on the screen. So, such visualization software running on PCs can be used for man machine interfaces. Sometimes, especially for power applications, you have remote terminal units, that is basically the system is working in, let us say, unmanned stations, and from kilometers away you want to get a view of what is happening, let us say which of the transmission lines are on, which are off. So, such a system is called a supervisory control and data acquisition system, often called SCADA. And so, SCADA systems with RTUs gives operators a visualization of what is happening quite far away in unmanned places. They are also MMI, they also have MMI purpose. Sometimes you have panel PCs, they are special types of PCs with touch screens, so that the operator need not type, he can just for basically convenience, because an operator has to concentrate on the process and should not be bogged down with it should be as easy for him to give commands as possible. So, people use devices like touch screens in such environments. So, for example, these are so there could be a variety of man machine interface kind of devices which needs to be interfaced with a PLC, starting from operator panels to monitors to PCs to keyboards to printers. So, all these it is possible to interface. Then you have to have programming devices, and this is a typical programmer. Programmers are of two types, either they could be handheld, which you can take to the shop floor and directly program the PLC, or they could be tabletop, where you have, which are of higher capabilities, and where you actually develop programs offline and maybe go and just load it there, because these have very good program development environments also. Finally, another very important thing is communication. So, there are various types of communications available, as we have already told. For example, point to point, where you run direct wires from an input or output module to the actual device. There could be bus communication is actually internal to the modules, or you could be network communications, where network or remote. These we have already explained. Communication technology could be communication medium can be various. For example, it can be radio, it can be coaxial channels, it can be fiber optic cables. So, different physical media may be supported, are supported. Various protocols are supported, for example, RS-232, 420 milliampere current loop, for RS-482, 485. These are point to point communication protocols. Apart from that, there could be network protocols. For example, industrial Ethernets are sometimes used, where the computational requirements are well known, well understood, and that due to that is CSMACD media access protocol, you are not going to get performance is not going to degrade. You have a field bus, that's a new standard for networking in the industrial environment, which we shall be studying it much more detail. There are other less popular, probably I can call them less popular. For example, the CAN bus is much more popular in another application environment, that is automobiles. Field bus is gaining popularity in the industrial environment, and some buses could be proprietary. For example, Siemens has a bus called CNEC, which is a proprietary protocol bus. The advantages of distributed network I/O are well understood. Cost saving on maintaining integrity of high speed signals, because basically the advantages of digital communication, and the advantages of having an intelligent module near the machine. So, you can have good sensor diagnostics, fault can be much more, monitoring functions can be realized without overloading the CPU. You can do special functions like startup. So, in a sense, in such cases the PLC CPU really works like a supervisory system, and the actual controls is done on the spot. So, you have better centralized coordination and monitoring. So, we have come to the end of the lecture, and so we have, I hope you have got a fair idea about what makes a PLC system, and as is customary, again you have some points to ponder. So, think whether you can mention 2 distinguishing features of industrial automation tasks compared to, let us say, a task in a bank, which are also computational tasks which also communicate. Mention 5 major components of a PLC system. We have mentioned more than 5, so you should be able to mention 5, and distinguish between normal, distributed and networked I/O. So, here we end today. Thank you very much. We will meet again.